go. We're doing 10.6 today. Again, we have some vocabulary, but the three theorems themselves are pretty straightforward. The colors will come in handy. So using this, of course, we'll always start with our name, my Hawaiian honorific, and all I want as an objective is students will be able to use segments of chords, tangents, and secants. So it's a very simple objective today. So here's how it works. When two chords intersect in the interior of a circle, like this picture, each chord is divided into segments that are called, get ready, segments of the chord. That's all it means. So now we're looking at segments here. So AE is a segment, EB is a segment, EC and ED. So it's just the parts where they cross, okay? If two chords intersect in the interior of a circle, then the product, which means we're going to multiply, of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. So here's the beautiful part. So it's going to be EA times EB, right? That's the product, is equal to EC times ED. So I'm going to do some color coding. So this one times this one is equal to this one times this one. That is our first theorem. We're going to do 3 of them today. Here's some examples. If you have these, they intersect inside the circle. That's the situation. Then you know that this times this is equal to this times this. It's pretty simple. We go 2 times x plus 1 equals 3 times 4. Okay. If I would personally divide both sides by 2, subtract 1, and you get x equals 5. Ta-da! If you want to check it, take that 5, put it in here, you get 2 times 6, which is equal to 12. So, you know, I'm always in the habit of checking. Now this one here, I've got x's in there, but that's okay. Same thing. You're going to do mn times nl equals kn times nj, or jn. So it's going to be x plus 2 times x plus 1 equals x times x plus 4. And this is where I was saying some of your algebra is going to come in here, going to kick in, and you are going to remember our acronym. When you do binomials, you have to do the first terms, the outside terms, the inside terms, and the last 2 terms. So here's your first 2, here's your outsides, here's your insides, and here's your last 2. In other words, everything multiplies everything else. So this will give you x squared plus 1x plus 2x, and then the last 2 is plus 2. And on this side, of course, it's just straight distribution. The x multiplies both things on the inside. And the beautiful thing about this is you have an x squared on both sides of the equation. So I'm just going to subtract x squared from both sides. Okay. In the meantime, I'm going to combine these two like terms. This is 3x's. So you have 3x plus 2 equals 4x. If I subtract 3x from both sides, I get x equals 2. Now, not done yet. I got x equals 2, but that's not what it asked me to find. It said find ML and find JK. So as you know, when we put our answers into big ideas, we always want to put the answer that it's asking for. So ML is here to here, and it's going to be all of this. So if x is 2, right, then this part's 4, and this part's 3, and 4 plus 3 is 7. The other one is asking for JK. So JK is here. If x is 2, then this is 2, and this is 6. So this is 8. Another way to check would be to take this 2 and put it in here. And so you'd get 4 times 3, that'd give you 12. And if you put the 2 in here, you'd get 2 times 6, also 12. So you know that that gives you this equality. It makes that equation true. There we go. Any questions? Now's the time. Yes, Anders. Scroll up like this or like this? Like this? Sure. All right. So there's our first theorem. Now the second theorem, first we got to talk about vocabulary, because our pictures are now going to be outside. That's inside. These are outside. So a tangent segment is a segment that is tangent to a circle at an endpoint. So this right here is tangent at A. That is a tangent segment. Okay, so here's the endpoint, here's the endpoint. Make that whatever color you're coloring it. A secant segment is a segment that contains a chord of a circle and has exactly one endpoint outside the circle. So here's our endpoint outside the circle. Here is the chord that it contains. Okay. But it's a secant, so it's all of it. But the definition is you've got one endpoint out here, and it contains a chord inside the circle. That's a secant segment. And then third, we have what's called an external segment. So I'm going to do this in green. It's the part of the secant that's outside, just outside. So this is just here, EC, just the outside part. So let's write down what they are. Blue is the EA segment. Red is the ED segment. And then the external is EC. And those labels should make sense to you. They're not crazy. So here we are at our second theorem. And this theorem uses all this vocabulary. If two secants share the same endpoint, here it's E, outside a circle, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external secant. And so this is what it looks like. Here's what it says. EB times EA is equal to ED times EC. Let's mark this up here. The product of the lengths of one secant segment, that's this, and its external segment, that's this. So product means multiply. That's what it's saying. This is the product is equal to the lengths of the other secant segment, that's ED, and its external segment, so that's EC. So you may even think of this as like if you wanted to put it in words, you could think whole times outside equals whole times outside, something like that, right? Where you end up thinking in words. However it makes the most sense to you, that's what I want you to write down, okay? But I will be turning the page in about 10 seconds. Okay, so that's the segment. So we're going to do some examples of this. And the third segment is just like it. So it'll be very similar, okay? All right, so example 3, here's what the theorem says. It says that RQ times RP is equal to RT times RS. Again, if you want to color code, it's the whole part times the external equals the whole part times the external. So the whole part here is 20, and the outside part is 9. The whole part here is 10 plus this x. And then RS is 10. So we have an equation, and we can solve it. That's 180. This 10 will multiply both on the inside. I'm going to subtract 100 from both sides, and I get 10x equals 80, and it wants me to find x, so I'm good with that one. This one's going to take a slight bit longer. That's why I wanted to spend a little more time on this one. But again, color coding here would really help if you want. RQ, RP, T. Can't be too careful, you know, especially when we're taking our notes. You can't be too careful. Because you might have a lot on your brain already, and this might not sink in quite yet, but when you see those colors, the next time you check it out, maybe you don't do the work until Monday. It should, you know, ring a bell. So same thing here. Now this is going to be a little trickier because we've got more x's, but it's the same concept, right? We're going to do the long part times the outside part equals the long part times the outside part. So the long part here is x plus 2 plus 3 more. So the long part is x plus 5. And then the outside part is 3. The long part here is all 4 of these added together. So all 4 of these added together is x plus 1 plus x minus 1. That's just 2x. And then the outside part is x plus 1. Some of you will be able to work a little faster than this. That's okay. I'm just taking my time because I don't want to rush. But you'll notice now that I have things I can distribute. So the 3 is going to distribute here, and the 2x is going to distribute here. Let's see what we get when we do that. Okay. Now, we have 3x plus 15 equals 2x squared plus 2x. This is going to be a problem. You may recognize that as a quadratic. Anytime you have an x squared thing and you can't undo it with a square, a square root, which you can't here, then your best strategy, okay, and this is part of why this lesson is going to take a little longer. If you want to solve a quadratic, first of all, it has to be in standard form. And standard form is this. It has to look like this and be equal to 0. So the a and the b and c are the numbers in front. They're the coefficients. But you have to have everything on one side of the equation and a 0 on the other side. So there's like 2 different ways you can solve it once you get it that way. You can factor and then use the zero product property, which I will go over, or you can use the quadratic formula. But that's messy. If you can avoid it, we're always going to try to factor first. So first, let's get everything on one side, which means I've got 2x squared. I always want this to be positive, so I'm going to move these over here. So if I take away 15, it'll be minus 15 over here. If I take away 3x, it'll be minus x. So it'll be 0 equals 2x squared minus x minus 15. And now this looks like this, where a is 2, b is negative 1, that's the coefficient in front of x, and c is negative 15. And so what we're going to try to do is factor this. That's the easiest way to do it, is factor it. So factor means you're going to put it into 2 binomials. It's the opposite of FOIL. Okay. So the first thing I'm going to concentrate on is this right here. This times this, the first 2 terms have to multiply to give you 2x squared. So what's the only 2 things that can multiply to give you 2x squared? Someone volunteer.
X.
And
2x.
Yeah. That's the only way you could get 2x squared, by doing x times 2x. Beautiful. Okay, second step to factoring, if you don't remember, is that these 2, this one here at the end, these 2 numbers here have to multiply to give you negative 15. Well, so then I'm going to come over here and I'm going to go, all right, what are all the different ways that I can get 2 numbers to multiply to give me negative 15? I can do negative 1 times 15, and I can do 1 times negative 15. I can also do negative 3 times 5, and 3 times negative 5. Those are the only 4 possibilities. There's no more than that. I mean, integers, you know. The way I know which one to pick, then, is that the combination of these, when they multiply, when I add them together, they have to give me the middle term. So these numbers have to multiply to give you the negative 15, but add together to give you the negative 1. Nothing in here will do that. That'll give you 14, that'll give you negative 14, that'll give you a positive 2, and that'll give you a negative 2 when you add them all together. So you might think, well, this is sort of a bit dead end, but then you remember, oh yeah, when I do the outsides and the insides of FOIL, these 2 will multiply each other because they're the inside terms, and these 2 will multiply each other because they're the outside terms. And when I combine those, that's where I'm going to get a negative 1. So I will eventually figure it out. This is not going to work. This is not going to work. But I do know that if I multiply, if I add this right here, if I multiply this with a 3, this will give me 6x. And then if I put the other number, 5, these will give me 5x. So 6x and 5x can combine to give me a -1 if this is negative and that's positive. Because now I have -6x in the middle, and I have plus 5x in the middle. And when I combine them, I get a -1. Plus, when I do -3 times positive 5, I get -15. So this is how this is going to work. Some of you are probably like, oh yeah, I remember this. And some of you are like, oh, I can just hear it. I should take a poll, but I don't want to stop notes. If I was in class, I would say, all right, raise your hand if you were the first one. Oh yeah, I kind of get this. And then stop, and then raise your hand if you're the second one. Now, we're going to keep going. Like I said, don't want to overwhelm you, but we just factored it. And now we're going to use the zero product property. What the zero product property says is, can you remember? This times this, these are two numbers, right? And this times this product gives you 0. So the only way you can actually get 0 when you multiply is that something has to be 0, right? Either this is 0, so the product is 0, or this is 0, so the product is 0. So the zero product property tells me at this point, I can say, well, what value of x here will make this equal to 0, or what value here will be equal to 0. And then you just solve the little equation, and there's your solutions. Usually in a quadratic, whatever power you have, your highest power, that's how many solutions you're going to get. So this is a 2x squared, which means we're going to get 2 answers. This is x equals 3. And this, if I take away 5 and divide by 2, gives me -5/2. It said find the value of x. If I put in x equals 3, this is 0, I'm good. It makes it true up here. However, can I have a -2.5 distance over here? Can x be a -2.5 in this circle? No. So sometimes you'll get an answer, but it doesn't work. It doesn't give you a solution that makes the equation true. So even though we got this answer, we're not going to enter that into big ideas. Okay, that's not going to give us a true statement. So it's x equals 3, and that's it. So any questions right now? All right, the third theorem is just like this one. If a secant segment and a tangent segment share an endpoint outside the circle. So here's the endpoint, there's the tangent, there's the secant. If they do, then the product of the product of the lengths of the secant segment, that's this, and its external segment, that's this, equals the square of the tangent. So it's just like the other one, except that there's only one external. So it's ED times EC equals EA times EA. I always thought this was like elegant. So it's going to be EA squared, EA times EA, equals ED times EC. So we can still color code this just like we did before. You've got your tangent squared equals the secant segment times the external segment. hopefully you can see how it's very similar to the other one. So again, this is a picture of fish in a tank, and we are going to do this. Here's the tangent, and here's the secant that goes all the way across. So find the radius of the aquarium tank. Here's the radius, here's the radius. So with this theorem, my tangent is 20. So it's going to be 20 squared equals the whole length is 8 plus r plus r. 8 plus r plus r. So that's 2r plus 8, that's the whole length, times the external segment, which is 8. We'll distribute, and we'll be able to solve for the radius. So 400 equals 16r plus 64. Let's see, when I subtract that, that's 336. And when I divide that, I get 21. Times 21, which is a reasonable number, especially when that outside one is 20. So this is the chance where I let you catch up and I say, any questions? All right. So, last problem. This is where we're going to spend the most of our time as far as examples go, because we're going to end up with a quadratic. And you'll have examples like this in class, in your assignment. So I'm going to use all this space. Try not to write too large is what I'm saying. Okay. So RQ squared is equal to RT times RS. 16 squared is equal to RT, which is going to be x plus 8, all of it, times x. That's where we start. Not too bad, right? And then we're going to distribute our x. So we get 256 equals x squared plus 8x. So again, now I have a quadratic. I have to make it into this form here, ax squared plus bx plus c equals 0. So to make it equal to 0, I'm going to move the 256 over here. Okay. And I'm going to tell you right now that I can't factor it. I would go through all of the factor pairs of 256. I'd see if I can combine any of them to get a positive 8. Trust me, there aren't any, but that would be a step you would try first. But because we can't find any, then we have to use the quadratic formula. And so we're going to write the quadratic formula up here. I actually saw this on You Think You're Smarter Than a Fifth Grader, that show. And they asked all the adults if they could say what the quadratic formula was. And strangely enough, they couldn't, because this is how I always remember it. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And in this case, a, b, and c, all of these are just the coefficients that are in front of your standard form quadratic. So here, a is 1, b is 8, and c is negative 256. And so this, and some of your calculators, if you have a big graphing calculator, you can just pop it in there, it'll solve it for you. But for the rest of us, we take this a, b, and c, we put it in this equation, and it gives us x. Now, of course, x is rs, so that's our final. So we're going to go from here plug it in there, and get our x. Of course, grab your calculator. So x is equal to negative b plus or minus square root b squared minus 4ac all over 2a. So I did skip a couple of steps because I did these together and this together and this together. But you would do this also on your own. And I would do 64, I add that together. Let's see, that gives me 1088. And then I have over 2. I would have to, of course, reduce this. And it does reduce, whoops, to 8 times the square root of 17 over 2. And I would reduce by dividing this 2 into both of the 8's. So x is equal to negative 4 plus or minus 4 times the root of 17. It's not pretty. That's why you can't solve it, though. So if Big Ideas asks you to put an exact answer in, you put in one of the solutions is negative 4 plus 4 root 17, and the other solution is negative 4 minus 4 root 17. However, that negative, that's going to give you a negative distance again. So I would only put in the positive, which will be negative 4 plus 4 root 17. If it says round to the nearest, say, 10th, then you could just pop it in your calculator and get that decimal approximation of about 12.49. Okay, and if it says round or approximate, then it's okay to have your calculator. Okay, but just remember, exact means leave it in the form of your square root. Approximate means use your calculator and round it. And so, again, this is where I'm going to ask you for questions, but we're done.